All right, this is a quick look at remote limits quiz number 4 over section 2.4 rates of change. It was very brief. In fact, it was just a one problem with 4 parts, just to kind of cover average rate of change, instantaneous rate of change, and what can you do with tangent slopes once you have them. Let's take a quick look at these short but sweet quiz limits number 4. The first problem asks for an average rate of change, which is really just slope. Um, you take the endpoints of your intervals, 0 and 4, you figure out what the y values are, so you have full points, you can do y minus y over x minus x, and so you can see that we determined value, the y value for 0. We determined the y value for 4. This is an area where some of you guys got in a little bit of trouble because you either didn't label what you were finding, which is really important, or you didn't show the full work of how you were determining those values, which of course is also important. You got to show your work. But once you have your points, 4, 67, and 0, -5, it's just a matter of plugging those points in and letting algebra do the rest, right? 67 minus -5, 72, divided by 4 minus 0, 4, 18. That's your average rate of change. We know that cubic functions are either going to look like this or like this. I mean, it's positive cubic, so it'll be one of those. If 0 was here and 4 was here, then our average rate of change is really just the slope of the line connecting those 2 points. And that's really all there was to it. Um, number, well, part B, I guess you should say, B is not a number, was asking for the exact rate of change of the function at 2. So this is where things get a little spicier. Um, we're going to take our function f of x, and we're going to have to apply the difference quotient to that function. And specifically, this problem has to do it at x equals 2. So I'm going to plug 2 in for a on this particular problem. Um, that means I'm going to need to evaluate f of 2, which we certainly did right here. Um, looks like f of 2 is equal to 7, so the point 27 is the point where we're trying to find the exact slope of the curve at that point, the instantaneous rate of change. Um, but to make this work, I have to take that value h. Remember that tiny little distance to the next point? So it's like I can't algebraically find a slope of one point. So this is where we use the secant slope, and then we take the limit as the points approach each other with that h value getting tiny, 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 right? We're going to make h approach 0. And so this is where the algebra really comes in, because I got to plug 2 plus h into our favorite function up here. So 2 plus h has got to be cubed, 2 plus h has got to be multiplied by 2. And of course, the tricky part was the cubing part. This is what you should have come up with. Okay, multiplying by 2 here was pretty easy, but the cubing part um, was going to be a little bit trickier. And I think what I saw a number of people doing, and this is the way I kind of worked it out in some of the examples that we went over previously, is maybe you do 2 plus h times 2 plus h squared, so you square it first. And squaring 2 plus h is much easier. You just get 4 plus 4h plus h squared. Then you can multiply the binomial by the trinomial, and a couple of those pieces end up getting put together. And so you end up with the 4 terms that you see right here. And if you need help with that algebra, you can always reach out. But it really was just algebra, and most of you guys did pretty well with it. Once we have our two expressions that we really need, we're going to substitute them in. So we're going to take, we need f of 2 plus h, and we found that this is what it was right here. So we're going to plug that in. And we also need, we needed f of 2. which we found F2 right here, right? So we plug that in. We know that when we use the difference quotient in this way, we need anything without that h to go away, because our biggest goal is to get rid of this h. I cannot evaluate a limit that approaches 0 if I have an h in the bottom, because that's going to create a 0 in the denominator, which is not ever allowed. So sure enough, um, we get the 7's to go away for us, and the h can then be factored out, which we see in this step right here. And then once you get rid of that h in the denominator through cancellation, we can evaluate it. Now, there were some people that once they plugged the 0 in for the h values, forgot to not write the limit anymore. Once you put the zeros in this step right here, you've evaluated the limit. You're not taking the limit anymore. Get rid of that limit. Some people forgot that, and that's just kind of understanding what limits are and what they mean. So be careful with that. But it looks like 14 was the exact rate of change. Okay. I guess we could discuss the implications graphically of what that is really quickly. So why don't we do that? All right. So here's what I did. I went into your TI calculator, or I guess probably more accurately mine, and I graphed our function, x cubed plus 2x minus 5. And it's just a little idea of what we just did. What we just did is we found two different rates of change for this. One of them was an average rate of change. And so to find that, what we did is we took the interval from 0 to 4. So the interval from 0 to 4 would have covered this territory right here. That's our interval, right? And I had to find some y values. So at 0, I think we had negative 5. And I think over at 4, I was way up here. Okay, so I guess I would have needed to go up further to really make this a better graph for you. But then we found the average rate of change between those values, um, which would have been something like that. Okay. Then in part B, we went to the point 2, and we had to find the value again. I think we found it was 7, 2, 7. So that was that point right there. But this time, instead of finding a secant graph that's going to cross this curve 2 times, we wanted just the single tangent graph, the tangent line that was going to skim it, and it was going to look more like that, right? Notice right now it looks like the pink line is steeper, but that's because I didn't get the point here graphed correctly. So I'll fix that for you in a second. We could easily have found the equation of this secant line, because we already had the slope was 18, and we already knew that the intercept was -5, because we found that at 0, right, at 0, the y value was -5. And so the equation of that would have been y equals 18x minus 5. And I will go ahead and graph that one for you in a better graph. And then we'll graph the tangent line, and we'll kind of see how they compare. So that's going to take us to part C. And in part C, it asked to find the equation of that tangent line at x equals 2. So the good news is we already found all the information we need. From part B, we found out that f2 is equal to 7. And so that is your point. It's just 2, 7. That's just the point, 2, comma 7. By the way, I noticed some people were writing points like this. That's not a point, that's an interval now. That's the x interval, from 2 on the number line out to 7. and then we probably would plug in to find the y values, and that's not what you mean. Make sure you use parentheses when you talk about points. But we're just going to go down here and plug in the information, the tangent slope we found in part B, and then the point, the x and y values 2 and 7, and we found an intercept of um, negative 21. Most of you guys did a very nice job on that, and that's the equation. Y equals 14x minus 21. And I think we can compare our two graphs now. The other one was 18x, right? 18x minus 5. So since this ended up being um, not as good of a graph as it could have been, let's go ahead and throw it out. And we'll come back to our graphing calculator and change that window and go up quite a bit further. Maybe we'll go up to like, oh, I don't know, maybe 100. All right, I think we'll get our value on there now from 4, right? So now that we have our graph, we know that the secant line was 18x minus 5, and you can see there it is hitting 0, um, negative 5 down here on the intercept for us, and then 4, 6, what was it, 67 way up here. So you can see it hitting twice, but then we found the tangent line, and the tangent line had a slope of 14, so it'll be a little flatter than the secant line. And it had an intercept of negative 21. And look at that. Notice how that one, it is just a little flatter, but notice how it's only skimming the graph right here at one point. So there you go. Seeing those intricacies there. Now, there's one last activity here. What we could do is we could go ahead and through this point of tangency right here, through that point of tangency, let's find the normal line. So it's going to be perpendicular through that. This is another piece of the problem that I thought you guys did pretty well on. Most of you guys immediately knew that you needed a perpendicular slope, and the opposite reciprocal of 14 is negative 1/14, and so you dialed up the correct slope. We're still using the same point. We're still using the point 27, and so we're just going to plug in, and you ended up getting 57ths or 7.143 if if you want to use that. So let's go ahead and just as one last thing here, plug that in just to kind of examine it. So for our last slope, we'll do negative 1/14 x plus 57. So I'll go with 57ths just because it's an exact value instead of the decimal approximation, 7.1, whatever, right? So here we go. It should definitely go through this point right here. Whether it looks perpendicular or not is somewhat suspect because notice we've only got an x scale of about 20 total units, and then we have a y scale of over 100. So yeah, that didn't look. It looks like a horizontal line. So maybe I need to put my x in the top up here. Make it work right. Yeah, that's a little. No, it's still looking horizontal. Actually, you know what it is it's just so flat. That's what it is. If I zoom in or square this out, it'll probably look a lot more perpendicular. I just think it's such a flat line, it's barely moving. It's not even changed. It's only changing point, 2, I think, from here all the way over to here. So that's probably why it looks so strange. But it doesn't look perpendicular because we're not squared off. Check this out though. If I hit zoom square, it will, and I think it's way down here at the bottom, it'll make it so that anything that's perpendicular or circular suddenly looks like the way it's supposed to. So you can see we lost huge amounts of our graph here. We don't really see a good secant line anymore because we lost the intercept. But if you look at this area right in here, it really does look like a right angle now. Okay, so that was the quiz, 5 points each, and like I said, a lot of people did really well. Just some cases, minor errors or just the lack of a little bit of work. There were a handful of people that turned in this bonus. I don't blame you if it didn't seem too much fun to you, but it talked about this slightly more complex equation that described how Comcast's internet capacity increases throughout the day. And if you graph this thing, it was kind of a fast moving and then slower as the day goes on. But creeping up towards 100% capacity, which has been my problem for the last 2 months. They always kick me off when it gets too high. So what are we going to do? Well, variables are a little different, but don't let that confuse you. You know, they're using T instead of A and P instead of F, but here's our function. So 4 is how many hours past 9 o'clock is when they said they started. So from 9 a.m. to 1 p.m. is 4 hours. So we're going to use 4. And there's really nothing you can do to simplify P of 4 plus H. Now, on the other hand, because 4 is perfect square, I can simplify P of 4. So we just get 70. And that's where we pick up here with our shaded work. And you can see immediately that 10 minus 70 is negative 60. And what I did, and a couple of you guys actually did this, so good thinking, I factored the 30 out from the top, and then I just dumped it out front. I don't make you guys show this step right here. I just put it in for formality. I'll really just let you say, oh, there's a constant in here. I'm just going to pull it out front. But it does make all the numbers so much smaller. Instead of dealing with numbers in the hundreds and even thousands, you just end up with small numbers. The trick for any kind of a square root function limit usually is going to be conjugate. So the conjugate of the square root of 4 plus h minus 2 is square root of 4 plus h plus 2. And so I multiply it by that. When I multiply these, the square root goes away because I'm squaring the root. And then these just become a 4, and then the middle terms cancel out. And so I just get 4 plus h minus 4, which just gives me the h on top. And that's what I wanted, because remember, from the very beginning, I had this h in the bottom, and it wasn't going away until now. Now that I have just an h in the top and then the h in the bottom, those will cancel. And you can see that at this point, it becomes available to evaluate the limit. I plug the 0 in, and I just get 30 times 1/4, which turns out to be about 7.5. So 7.5% per hour. Remember, this was an application problem, so you got to use units. A couple of people lost a bonus, one of the bonus points, because they forgot the units. But at 1 o'clock exactly, the Comcast internet capacity is increasing at exactly 7.5% per hour at that point in time. Some definitely number of people picking up some bonus points, so nice algebra, nice work on that. And good luck on the quiz today. The kind of summative quiz probably be a little bit longer and cover a little bit more of everything, but get through that quiz, enjoy it, have a lovely weekend, and we will see you next week.